Yeah, okay, so it has started recording. Okay, so let us start. So till now we have, or till yesterday we have completed that applications of coordinates. So basically detection and segmentation. So today we are going to get into a very new thing, which is recurrent architectures. Okay, so this is the agenda as always. Okay, it's a bit lagging. I'm not sure. Let me just once more share it. De-share it rather. It's a bit of lagging. 1 second. Yeah, now it should be okay. Let us see. Yeah, it's a bit lagging, but it's okay. Okay, so this is the agenda. So understanding models involving sequential inputs and outputs, basically, and then using recurrent neural networks to deal with sequential outputs, inputs and outputs, and from RNNs to LSTM. So recurrent neural networks that we all sometimes call RNN, and from RNN to LSTM. So these are advantages and disadvantages of RNNs for sequential inputs, and then how do we deal with the disadvantages with LSTMs. The resource, as always, I am giving the resources, and I'm almost diligently following Sergey Levin's lectures, this CS W182 course from UC Berkeley. The link is there. This particular topic is mostly taken from lecture 10. Next week, we will do probably lecture 11 and 12. Okay. So let us basically delve into the business. So what we have till now seen is basically you have one single input. It may be a big image, even a big video, but we have a single input. I mean, it is not changing sequentially. Okay. At some time you are having one input and then again another input, then again another input, and so on. That is not the case. But suppose some image is coming, you have this big coordinate, you have finally this classification layer, and it outputs this categorical variable with some probability, say cat with 64% probability, or dog with say 1% probability, something like that. Okay, so that was the normal use case. But now let us think that we have some sequential input. So there are say 3 examples given, x1, x2, and x3, but each of them have say different length inputs. So basically by length, I mean how many elements of the sequence. So this is x1 is a sequence and it has 4 elements. This has 3 elements. So 1, 2, and 3. X3 has, I think, 5 elements. So we are denoting it is in this way, that x11, where the first subscript tells the input basically, or the sequence number, and the second subscript tells the element of the sequence. So this has 4, this is 3, and this has 5. Suppose if you have such an input, so not just xi, and then what will happen? I mean, what is some example of this? One very typical example is classifying sentiment for a phrase. So the input can be sequence of words. So it may be some one sentence or a phrase, and you have to say that, okay, if it is a positive sentiment or negative sentiment, or even more fine-grained ones, that okay, it's a sad one, or it's more or less say neutral or happy one. I mean, it's laughable, etc., etc. So these are classifying sort of the sentences. Okay. Similarly, classifying the activity in a video. So we can think that video is a sequence of frames. So we can actually process the frames one by one. So in a sequential manner. So it may be that, okay, one video is content of 4 frames, or maybe one sentence or one phrase contains 4 words, one phrase contains 3 words, and so on. So how do we basically classify them? So that is what we have asked, or we will be looking into it, this topic. What if we have variable size inputs, right? So what can be some simple idea or naive idea? From there, we will go into more sophisticated ideas that we will see. So yeah, so these are the inputs. Now, simple idea is basically 0 pad up to length of the longest sequence. So what this means is that you take the longest sequence, say the longest sequence is say 6. I mean, whatever is your are your x1, x2, x3, x5, sorry, x4, x5, x6, etc. That is the sequences. Let the number of elements of the sequence, or the number of words of the sentence, in another example, maybe it's say 6. In that case, you know that no sequence is more than length 6. So what you do is, okay, let me take one sequence, let's say this one, x2, and then I can basically replace all the missing elements till 6 with some default vector, let's say all 0. So I have to say represent these elements. For example, if it is a word of a phrase, I have to represent this word with some vector. That way it will be given as input to the neural network. Okay. It can be a frame also. That frame you can even just pass it through a convnet. Let's say you have a convnet which is pre-trained on image classification task. Say it was pre-trained on ImageNet, and then you have a video and you want to basically represent each frame with a vector. How can you do it? One simple way is to pass this through the pre-trained ImageNet, I mean ImageNet pre-trained classifier, convnet, and you take it from the, say, last layer of the convs. So for a VGG, you know, that was 7 × 7 × 512, right? And then you basically arrange them or organize them in a big length vector. I mean, all these 7 × 7 × 512 numbers, you just put it in a long vector. That sort of represents or encodes the frames, each frame. Okay, so for each frame you will pass it, for each frame you will get this long vector. So what I'm sort of tried to convey in by these in this slide is that, or even sort of the first part of this slide, is that you can represent these elements of the sequence by a vector, by a long vector. Now the elements of the sequence can be frames, can be words, can be many other things. Now, so after you represent each of these elements with vectors in terms of vector, so you will have 4 vectors here, you will have 3 vectors, you will have 5 vectors here. But you have the longest length of the longest sequence, you know, is maybe 6, or you have assumed that it is 6. So what will happen to the 4th, 5th, and 6th vector? What will happen to the 5th and 6th vector, and so on? So we will basically replace them with some default vector, which is, say, all 0. So that's a very good choice. So 0 pad up to the length of the longest sequence, and then you basically concatenate each of them. So if suppose each of these representations, I'm just thinking that this is d-dimensional. So your length of the longest sequence is 6. So your if you concatenate all these 6 vectors for each of the sequence, it will be of 6D dimension. So this 6D dimensional vector you will give as input to a normal neural network that you have seen till now, and then you can classify, right? So that is one naive way. So how do you deal with these sequences? As it is said, it is very simple, but does not scale well for very long sequences. And you can immediately see why. Because if it is very long sequence, if it is 1000, basically, maybe the length of the largest sequence, and then 1000 into 7 times 7 times, say, 512, these many numbers you need to basically concatenate, right? So that, and then This you need to basically give input to this first layer, where you will have so many connections, so many weights to be learned. So it is not scalable. So if this is this big long vector, and suppose this is a 4096 hidden, the number of neurons in the hidden state, first hidden state, then itself this will have 4096 times these many weights to be learned. So it is not scalable. So this is simple, may actually works well for short sequences, but it's not scalable. Okay, so this is the naive idea. Now, what can you do? What else can you do? Another thing is one input per layer. So we have earlier seen for normal, say, neural networks that we have sort of dealt with till now, input only is given to the first layer. There is no input in this, or rather, no external input to these layers, not these or these or these. So what happens is that these are connected. So the input to this layer is basically the output of the previous layer, which is the output activation, right? Output hidden activation or activation, whatever you can say. But this is basically the input to these inner layers, hidden layers. It does not get any input externally, okay, from external sources. That is what you do here. See, you have this first layer. I mean, earlier we were giving the input from say left hand side. I mean, we were visualizing or showing it from the left hand side, but here I've just placed it there, just so that it becomes similar with the other layers. So you have 4 layers for a 4-length sequence, and the first element of the sequence goes as input to the first layer, second element of the sequence goes as input to the second layer, and so on. In addition, it also has the normal input, like this one has the normal input, that is the previous layer's output, which is the activation coming from this layer. That also goes in here, right? So in addition, this layer is having another input. So except for the first layer, every layer has 2 inputs. One is coming from that element of the sequence, another is from the previous hidden activity out or hidden activation. And then you can basically simply classify it. So this is for a 4-length sequence, it is it has 4 layer. For 3-length sequence, it is 3 layer. For 5-length, it is 5 layer. Now, each layer, what happens is this. I mean, if, mathematically, it is very similar to what normal neural networks we have earlier seen. They are only HL minus 1, that is for a Lth layer. For Lth layer, the output from the previous L minus 1th layer, this goes to this or gets multiplied with this fully connected layer, or sometimes called linear layer. So W into HL minus 1, or sort of WL into HL minus 1 plus the bias. That's what we have seen to get the pre-activation. Then the pre-activation function goes through some activation. Sorry, pre-activation actually goes through some activation function to get the hidden activation in that layer. What only thing we are changing is that we are telling that we have the concatenated input, which is previous layer's output and this layer's basically the external input. So we are denoting it as HL minus 1, the previous layer's output, and this is say XIL or XIT. So ith sequence and tth element or Lth element. Okay, the T basically the notation comes from the connotation of time, and we will see. I mean, you can think that you can see why the time sequential data. So time, it has a time connotation. So maybe frame, if you think video frames, then okay, it is at different time the frames are coming. Okay, so that has a natural connotation. So but the major takeaway from this is that only these things this thing get changed in the equations, just this gets added, okay, as concatenation. Okay, I mean, then a naive or natural question would be, or obvious question would be, what happens to the missing layers. So for example, in this sequence, what will happen to the previous two layers or previous one layer, whatever many layers are there. Okay, so for this again, the idea of using zeros, right? So we can think that, okay, we have some sequence up to max length, and suppose your max length sequence is 6, then what you will assume that you will have 6 layers, and everything before these 4 input, that you assume the inputs as 0. Very similar to what the zero padding idea was there given in the naive idea. So this is so this is what is told as all activations prior to the first word or first layer are assumed to be 0. So it does not change anything in terms of the output. So it will not change anything if you just think that, okay, there were a 4-layer network for this, there was a 3-layer network for this, or there is a 5-layer network for this, because you are just adding 0, passing 0 previous to that. Okay. Now, this is more efficient than always zero padding the sequence up to the max length. What I mean by zero padding the sequence up to the max length is the first naive solution. So what we showed here is that simple idea that you zero pad up to the length of the longest sequence. But you see that, or you notice the problem that it is not scalable. But at least this does not require this very big fast layer. So here it is said, each layer is much smaller than the giant fast layer needed in case the whole sequence with zero padding is fed to the first layer. So whole sequence you zero pad to up to the length of the maximum sequence, and then you feed it as to a normal neural network. There your first layer of that normal neural network will be giant. I mean, it will have to cater for all the concatenated sequence vectors. Okay, so but at least this is more scalable. Later layers get more training. Now, what do we mean by that? So you have different theta parameters or W or B parameters. I'm just collectively telling theta as the W and B. So for different say theta L basically is WL and BL. Yeah, WL and BL. Okay, so this theta, so this has some theta L, this has some theta, and so on. So this will then suppose you just first you got this this sequence. So this one, so the theta for this layer, and this layer gets trained, because before that all are 0, right? Here it gets trained. I mean, these 3 gets trained. In addition, this gets trained. Here, these 3 gets trained. This also gets trained, and this also gets trained. So only the later layers get more training, because you have more such shorter sequences. The longest sequence is 1 or 2 or maybe very less. So this has a problem that even if you are using so many layers, you don't train it enough. Even if you have a lot of data, it may be that the longer sequences are very less. Okay, so that's what I mean by later layers get more training, but actually the earlier layers get less training. So that is another one disadvantage. I mean, though there was an advantage that it is better than always zero padding the sequence up to max length, but it is basically disadvantageous in this way. Okay, it may not work well with longer sequences. So also another thing is total number of weight matrices increases with the max length sequences. So I mean, this same disadvantage of if the sequence length is very high, then it becomes very deep, and you have to learn a lot of weights. Okay, so before I go to the solution, I'll stop for any questions. If you have any questions, please ask away. It was pretty simple till this point, but still, if you have any questions. Okay, if not, let us go ahead. So this is the idea then. So can we share the weight matrices? So what did we say? That these later layers get more training. So can we just enforce that, okay, the matrix, that is the weights are basically same in each layer. So even if the later layers gets more trained for shorter sequences, you have the chance that, okay, the same theta gets trained. Okay, so this is the idea that is used behind this. Can we share the weight matrices? So basically, what if WLBL for all the layers are same? So whatever W we use here, the same W we use here and here and here, okay, in all the layers. So this is called a recurrent neural network. So it's basically recurring. The weights are recurring. That, okay, this layer is identical with this layer, and this layer. Okay. This we actually, there is another notion or notation rather. A recurrent neural network extends a standard neural network along the time dimension. So this is I mean, this is the figure or image you will sometimes see, or probably many times see in papers or literature related to recurrent neural network. So you give some input xt, which is basically t can be from, say, 1 2 3 4, so t x1 x2 x3 x4 etc. And this circular arrow, what this means is basically that it has the layer has input as these x1 x2 x3 etc, and the output from the previous layer. So it's sort of the output activation from the previous layer that goes back to this layer. So that this is sort of notation again. I mean, you can just think of it visually like this, but in a, say, sort of convenient manner and compact manner, it is basically drawn as this. So this is a recurrent neural network. So again, just to summarize, what is the difference between normal neural networks and this recurrent neural network is that you have many layers, but these layers are all shared. That is, it all has the same weights and biases, same parameters, learnable parameters. And then you not only have input from only one or the first layer, inputs can actually come in every layer. Okay, and the input to every layer is basically two things. One is that external input, that is the element of the sequence. Another is this hidden activation, like the normal neural networks, hidden activations from the previous layer. Okay, so this is basically the difference with the normal neural networks. Now, it is not super clear how do we do back propagation for this. I mean, because we have seen for normal neural networks how to do the back propagation. We have learned it when we, I think it was in topic 4 or 5, whatever. But this was the figure that we used, right? So yeah, this is the normal neural network. I mean, the forward pass, what happens is that, okay, you have, say, the input X, it has in the first layer the parameters W1 and B1, weights and biases. It gets the pre-activation A1, it goes through the activation function to give the activation values or feature values, or sometimes it is called hidden activation, so H1. Then again, through the linear layer to get pre-activation, activation, again pre-activation, then in finally you have this output activation function, which is mostly I mean, for classification problem, it is say softmax. Okay, the softmax function, and then it gives the output as some fx theta. This f is the representing the whole function from this x to y, and we have some loss that we denoted as J. This was C was the true ground truth value or the true prediction, and fx theta is your sorry, this is the true value or true output, and this is the predicted output. this F, and you have some sort of a loss between them, right? I mean, in classification, it was cross entropy loss. So I'm not going into much detail of this. So for the purpose of this lecture, I mean, since we have many layers and so on, I'm just compacting the notation a little bit. So for brevity, bias is not considered. I'm not just considering bias, but it, I mean, everything basically extends to that also. So I have just given W1, W2, W3, etc. Specific names of the activation functions are shown. So I've just for your convenience actually to think about that. Okay, what is W1, what is G? Just I have given the name. So linear layer, the sigmoid layer. It can be sigmoid, it can be 10H, it can be ReLU, anything. But just one example. Again, linear layer, sigmoid layer, linear layer, and then finally, loss function is shown at the bottom as a function of output reactivation. So this JA3. So because J is a function of this whole thing, the predicted output, but this in turn is a function of all these things. Also, this is a function of A3 also then, right? So F is a function, I mean, this output Y is a function of A3. So I have just written J in terms of A3. I mean, it could have been written in terms of A2, H1, whatever. But I have just written it in terms of A3. So loss function is shown as, at the bottom as the function of output reactivation, which sometimes you, I mean, it can be called as logits also, right? The output logits. So this is the sort of notification. Now we will do a little revisit of it. So that will help us get more grasp about the of the backpropagation that happens in Rn. So what do we ultimately want is that for use in the gradient descent algorithm, we need the gradient of the loss with respect to all the parameters, right, in at each iteration. So you do the forward pass, you get all the pre-activations, activations, etc. And then you basically do the backward pass where you compute separately each of these. That is the derivative of the loss with respect to all the individual parameters. So I mean parameters of layer 3, parameters of layer 2, parameters of layer 1, etc. And that you then employ in your gradient update step, that is previous gradient, previous theta, value of the parameter minus step size times this gradient, right? So that way you update. But you need to get these loss gradients in the backpropagation algorithm, right? So, but okay, so again, just reiterating, this is normal neural network. I mean, we are sort of doing this backpropagation revisit, and then we will again come back to this RNN backpropagation where weights are shared. But now we are doing a little revisit. So what is del J del W3? I mean, if you use chain rule, it is del J del A3 because J is a function of A3 and then A3 is a function of W3. So del A3 del W3. Similarly, what is del J del W2? It is del J del A3 del A3 del H2 because H2 is a function of, A3 is a function of H2. Then H2 to A2, that is H2 is a function of A2. So this is del H2 A2. And then del A2 H1 or rather del A2 W2 because we are ultimately wanting the derivative of the loss with respect to W2. So this is just the chain rule. And again, I mean, we have told it earlier also that backpropagation is just an intelligent use of chain rule, right? So we get the del J del W1 also. Okay, so this is what we want to get. Now, how do we get it via backpropagation? That we'll see. Right. So we simply follow this rule. So what is the rule? First thing is that initialize something called del J del A3, which we are just denoting by delta. And what is del J del A3? If we just dig deep here, it is the derivative of softmax cross entropy loss with respect to the output activation, okay, or the logits, or the output pre-activation of the output layer, or sort of the pre-activation of the output layer, which I am calling the output pre-activation. and this cross entropy, sorry, the softmaxed output is basically the activation, output activation, and A3 is the output pre-activation, right? So then you do the cross entropy loss, you basically compute the cross entropy, and you take the derivative. So I have not given you the expression for what will be this del J and del A3 in where J is the softmax cross entropy loss. I mean, I forgot to upload it in the Bias or something, but yeah, I have that. So, but just believe me that it's not very hard. You get it, okay? Then after you initialize with this delta, what are you looking for? You are looking for del J del W3 first. First, you are trying to get this derivative of loss with respect to this W3, which is equal to this that we have seen using chain rule, right, from the last slide. This is just del J del A3 times del A3 del W3. So we are assuming that we have got the second term del J del A3. So what simply you have to do is you have to multiply del A, this thing with del A3 del W3. Okay. So that's what we are doing next. So you got this. Then for each layer with input X and output Y. So if you just closely follow this, you see that I have made all these things transparent. It is just this I am focusing into, right? So that's the same thing here. Okay, so for each layer, so this is one layer, right? It has linear layer name, the name is linear layer, it is sigmoid layer, it is linear layer, and so on. For each layer, just see what is the input and output. So input X and output Y. So what is X here? H2. And what is Y? A3. It is saying that if the layer has learnable parameters theta, of course, linear layer will have learnable parameters W. For sigmoid layer, there is no learnable component. For ReLU, you don't have learnable component. But for this layer, you have a learnable component. What will you then do? Then it says that del J del theta is you multiply your delta that you have computed earlier, that delta with the derivative of output with respect to the parameter. So output was Y, parameter is theta. So del Y del theta into delta. If you do that, you see that you get the same or where you wanted to arrive, basically this del J del W3, because in this layer W3 is the parameter, so the learnable parameter it has. So you just simply employ this rule. So with delta, which was this, you multiply the derivative of the output with respect to the parameter. So output was A3 and parameter is W3. So you get the del J del W3, that is from simple chain rule, you know that it is this. Then it is saying that I need to compute the delta next, which I will pass on to or back propagate to the previous layer. So what I am telling as previous layer is layers on the left hand side, and next layer basically layers on the right hand side. So you have got the delta from here in this layer. Now you will compute I mean the loss, derivative of the loss with respect to other parameters also. So you need to propagate this delta value. So that how can you do, or rather back propagate this delta value? How can you do? It says, the rule says that you multiply the same delta. So here, remember, you were multiplying delta with the derivative of Y with respect to theta. Here it is saying that you multiply delta with the derivative of Y with respect to X. So you are multiplying the delta that you receive to this layer, this delta with the derivative of A3 with respect to H2. So that's what if you do, you get this new delta that we will be using next. Please stop me if you have any questions in this part. Okay, I'm just sort of telling what we told in back propagation in a different way. I mean, there is some reason for that. I mean, we will go and see. Okay, so it is becoming so much lagging. I am again sort of resharing, just unshare and reshare. Somehow the network is lagging. Okay. Oh, the network is so slow today, but yeah, hopefully. Okay, anyway, so let us go ahead again. Okay, so yeah, please, I mean, raise your hands if you have any questions. Now, you basically repeatedly apply this rule now. So what you will do is you go to the next layer, you check whether each layer, what is the input and output of this layer? Does it have a parameter? If it has, then do this. If it does not, do nothing. And then always do this to get the new delta. Okay, so this layer we have now focused on. If the layer has learnable parameters theta, actually it does not have any learnable parameters theta, so you do no operation. Okay, so much lagging. Okay, yeah, okay, so now your next step, which is you basically prepare your delta to be back propagated to this stage, this layer. Okay, now so you have this I mean, you perform this. What is this? The previous delta, you remember what was the previous delta? It was this, right? So J with respect to A3 and A3 with respect to H2. So this part was your previous delta, and you actually multiply with the derivative of output with respect to input. So output is H2 and input is A2. So H2 with respect to input, right? So that way you actually proceed. I mean, I'm not going into this for the next layer. I mean, okay, I mean, one last time for this this layer, and then we'll skip the other two layers. So now you are focusing on this. It has the learnable parameters. So previous delta was this, and you are multiplying with the derivative of output with respect to the parameters that just comes from this rule. And you have earlier gotten this derivative of the loss with respect to this parameter by using the chain rule as this, and then you are seeing that this is the same thing by backpropagation that you are getting. Again, the next step will be to compute the new delta to be backpropagated. So the delta that you are getting into in a layer is the del J with, sorry, I mean, it's not this delta, I mean this delta. Any delta that is coming into the layer is the output, sorry, the derivative of the loss with respect to the output of this layer. And when you are done with the computation for this layer, you are actually emitting the derivative of the loss with respect to the input of this layer, which becomes the derivative of the loss with respect to the output of this layer, the previous layer. Okay. Now, okay, so this I'm just quickly skipping. I mean, it is just applying them for the other layer. So ultimately, you are getting this del J del W1, which you have got from the chain rule also. And this delta you will not use, but I mean, yeah, I will not go into it, but you can actually use it to optimize your X also with respect to the loss, and that has some other applications in explainability and so on, but I am not going into that. Okay, so so sort of the revisit is completed, and this is the summary. That neural network is a chain. We get delta from the next layer, and you remember what did I tell about the next layer? Next layer is basically the layer on the right hand side, which is back propagated into the previous layer. And this is the basically algorithm. You initialize the delta with the derivative of the loss function with respect to the last layer pre-activation. Then you repeatedly do this for each layer. If it has basically a parameter, learnable parameter, you multiply the previous delta with derivative of output with respect to the parameter, and then your new delta will be previous delta times dy dx, that is output with respect to input. And this is sort of the graphical representation of it. Whatever we have told here, we will come to the full graphical representation of this, but this is just the forward pass. So you have one layer which has x as the input, y as the output, and some functional relationship between y and x. That functional relationship for a linear layer is that y is wx plus b. For ReLU, it is the ReLU function that, okay, if x is more than 0, it will be equal to x. If x is less than equal to 0, it will be 0. So you have this graphical representation that you have an input x and you can have some parameters theta, and you are emitting an y for every layer. Okay. Now, what this backpropagation rule simply tells graphically, that you get this del j del y, that is the delta with respect to y, that is the output of this layer, and you get first the delta with respect to, sorry, the derivative of loss with respect to theta by multiplying with this quantity, and you also get the delta x. So delta with respect to x. So that's why it is delta x, and delta with respect to y basically means loss with respect to, I mean, derivative of loss with respect to the output. Okay. And for that, you just multiply this delta y with the derivative of the output of the layer with respect to the input. Okay. So this is basically a graphical way of showing this part, this backpropagation. Any questions in this part? I mean, this is just a revisit, but if you have any questions, please ask them. Okay, if not, then let us go ahead. So backpropagation for the shared weights now. Okay, so RNN uses shared weights that we have seen. So is there any change that is required for backpropagation? It definitely seems, because it is not exactly the same as the unshared feed-forward neural network, right? So and also it has these inputs, right? But that is easy. I mean, you just concatenate these different inputs with the activations for that layer. Activation input, you can say, for that layer. Okay, now what we can do is, okay, if we do this simple backpropagation, the normal backpropagation, then what we will do is we can just compute the del j with respect to, say, the del AO, the output rather, and then you are basically passing it through this layer, the delta that you are getting. Now you are multiplying with the del y of this layer with respect to the del theta, right? So delta into del y del theta, that gives you the basically the derivative of the loss with respect to the parameters in this layer, right? So you get the del j del theta. Okay, del j del theta. You basically compute the new delta, which is delta x for this. Then you are using this new delta for this layer to get the del j del theta again, because thetas are same. So here is also the same theta, here you have the same theta. So you are overwriting what you have computed earlier with this new one. So ultimately what will remain is the del j del theta that you compute for the first layer. So that is not right. You are not using these layers to compute the del j del theta, because the thetas are shared. This causes this problem. So we need to change a little bit this backpropagation algorithm, and this change is not much, as you will see. So we will go and see what is the motivation. I mean, it's a very loosely motivated one. I mean, it's not very mathematically rigorous, but I will point you to again Sergey Levin's lectures for this rigorosity. rigor, but I mean, at least for a two step RNN, I'm trying to show it. Before I go there, I see a question. I raised hand from Anupam. So I am asking you to unmute. Yeah, you have some question, Anupam?
No, sir, I just wanted to understand how do we do the back propagation? Like we talked about how we can represent the RNN as a also like an on a time frame, right? Like on a time dimension. So can we also like discuss how we would do back propagation along the time dimension?
Yes, yes, that's what we are discussing now. So that was a revisit for feed forward network, and then we have sort of told that if we try to use the the back propagation algorithm that we revisited, that is for the feed forward network for this RNN, then it fails in some way. That was the disadvantage. It gets overwritten, the del J del theta, and only the first layers del J del theta gets ultimately. So you are not using all these layers, other layers, later layers. So what changes you need to do, that I'm coming. Okay.
Okay, sir. Okay, thank you, sir.
Okay, you can, yeah, okay, so let me, yeah, okay, so what change to back propagation is required? So, okay, so this is again the graphical representation for a sort of two-step RNN, only say these two. Okay, so what is the first step doing? It is giving an input X, and then it has the parameter theta, which is the same parameter for the next layer also. I have not written H as a function of theta and X also, because we are not interested with the computing the derivative of loss with respect to X. So I have just omitted things that we don't need. And in doing so, what I have omitted also, I'm seeing there is a small mistake there. I should have given some X here also, but yeah, just think that there is one X there. Okay. Now, about this, so you have this H theta. So whatever is the output of this node is a function of theta. And as I said, it is also a function of X, but we are omitting because we don't need that for this purpose. Now, this next layer, which is also a shared layer, it gets input from this as this H theta, and this basically not the input, but it is parameterized by theta. So this output of this layer is a function of both the output of the previous layer and the parameters theta. Okay, so it is f theta, f or function of theta and h theta. Sorry. So function of h theta, that is this, and theta, which is the same theta that is used in both the layers. So this sort of gives you a very small recurrent neural network. So if we now put back or sort of remember what we used in our back propagation lecture also, this rule, if you remember, it is so if u is a function of x and y, both x and y, so u is what, this thing, okay, this output, where both x and y is a function of some t, right, some other variable, then this is the formula for getting the del u del t. Okay, so del u del t, you just think that your f is same here, x and y are your theta and h theta, and t is theta. So if you employ this rule, it is del f del theta that you want, because it is del u del t that is what you are wanting. So del f del theta, which is del f del theta, which is basically, yeah, so function of theta. So del f del theta and del theta del theta, that is what you have. If you just put it simply, you will get, right? And del f del h, that is the second component, and then del h of that theta. So now this del theta is 1. So you get this as 1. So what you ultimately get is this del f del theta is the previous del f del theta and this, right? So the only change that you require is basically in that algorithm. I think, yeah, it was there. Maybe, yeah, go back to this algorithm once. So this del j del theta, we were setting it to del y del theta into delta. Instead of setting, we will accumulate. Let's see. So yeah, just give me a second. Just give me a second. Somebody has linked. Yeah, instead of using basically this del J del theta to basically overwriting, that is previous delta into del Y del theta, what you do is whatever your del J del theta was, that is whatever del J del theta you have got from here, you just add it to it. So accumulate. So accumulate the gradients during the backward pass, right? So in most of the libraries, say PyTorch, TensorFlow, they actually do it. So you don't have to change anything for this. So much disturbance. Okay, 1 second again. Okay. Okay. So accumulate the gradients during the backward pass. So this then basically, I mean, as I said, most of the libraries already has this, so you don't have to change anything. So this is the small change that you need to do. So with this change for RNN, that is with shared weights, this is your backpropagation algorithm. So only this red part is changed. Okay. Any questions on this? Okay, if not, then let me just quickly go through this. I mean, I will just stop here. I think I can have time to, next Saturday to complete the other parts. Okay, so we have seen about the variable size inputs. So you have sequence of inputs, and the inputs can be of variable size. But what about the case of variable size outputs? So we can have basically outputs at every layer. So for example, this image description or image captioning application. So you are giving this image as an input. So the input is one single, but the output is these many words, and it can be different for different images, right? A crowd of people looking at giraffes in a zoo. It may be very different for another image. So it may not always have these many number of words also. So before we were getting an input at every layer, now we are getting an output at every layer. So it is basically this xi as the input. Then from every layer, you are getting this output. And for getting this output, you just use a readout function. So this one is what I was saying in the last slide, that at each step, you are doing this, getting this pre-activation by passing the previous layer's activation through this linear layer, that is WL HL minus 1 plus BL. Then HL, I mean, this part is very similar to the simple feed forward neural network. HL is, that is your activation you get from the pre-activation by basically passing it through the activation function. Now, what is the output? The output is at every layer you are getting an output, and this is just a readout function, some kind of a readout function, which basically means that you just functionally convert this HL to some vector. Maybe if it is say word, so you can think that okay, at every time step, or rather, yeah, I mean, this is the layers are also called time step colloquially. So at every layer, you are outputting a single word. And suppose your dictionary of word has 10,000 words. So you can actually output a 10,000 length vector where, sorry. Okay, so this is basically at each layer you have this some kind of this readout function, as I was saying. So you can have this 10,000 length vector, and this 10,000 length vector is basically a probability vector. So it gives the probability of each word in that dictionary. So we can have a loss at each y hat L, for example, cross entropy, because it's a classification. I mean, you can think of it as a classification problem. At each time step, you have some ground truth word, right? So that ground truth word, whether your predicted word probability or the probability for the probability for or the word which has the highest probability in your prediction, if that does not match with the ground truth word, then you basically compute the loss, which can be cross entropy loss. So you have at each layer or each time step this loss, which you sum up to get the full loss. So we will see tomorrow how we will, so not tomorrow, Saturday, how we will use this loss, this whole loss to be back propagated through this neural network, recurrent neural network, to get it trained. So what we have done today as summary, we have defined defined RNN, that is recurrent structure, recurrent neural network. And then we have seen that what changes are needed for the backpropagation. Now we have just started the recurrent neural networks with multiple outputs, and we will see what change that will require. Okay, I think I'll conclude here. If you have any questions, please ask. Oh, the slides are already up, so you can read ahead and maybe make yourself comfortable for the next class. Any questions from anybody? Yeah, I think Anupam has some question. So I am asking you to unmute. Yeah.
So maybe this question is not valid, but sir, how does the back propagation algorithm compare to neural networks with skip connections?
Oh,
Like,
skip connections, I have not basically told it the back propagation. I mean, I have not rigorously told, but you can find it in the book. But it's not much different. You have to just do this analysis that, okay, you have, it is a function of hx and x, okay, and then you, because that is the input, it is not, I mean, in our case, x is the thetas. That case, it was, sorry, hx plus x. And then you can do the derivative and you will get it. Okay. So I have not discussed it.
but sir, is it similar to the back propagation algorithm for
Yeah,
RNN?
it will be very similar. It will be very similar. You have to just do the math a little bit. Nothing.
Okay. Okay, sir. Thank you.
Anything else? Okay. If not,